Let's use an unorthodox method to help you master the most common solution equilibrium graph problems in second-year high school chemistry. After watching this, you can solve problems right away. Let's get started. Okay, so first, how do we quickly solve these types of graph problems? There's a secret here. All these graphs have a K point. What does that mean? It means that from a single point, we can calculate the equilibrium K value of the solution. So let's get straight to the conclusion. For the simplest titration graph, its K point is the starting point. Everyone should know this. A slightly harder one, you've seen this type of graph, is called a particle distribution coefficient graph. The K points are these two intersection points on the left and right, corresponding to Ca1 and Ca2 of the diprotic acid, respectively. The hardest one is this type of logarithmic graph, which is quite complex. The K point is found where the x-coordinate or y-coordinate on the graph is 0. For example, in this graph, the point where the x-coordinate is 0, these 2 points correspond to K1 and Ca2 respectively. This graph is very clear, right? The 3 0 points correspond to K1, K2, and K3. Okay, so how exactly do we calculate these K values? Let's go through them one by one. First, for the titration graph, it's the simplest. In this graph, the problem statement tells us that we are titrating acetic acid with sodium hydroxide, right? Since it's the starting point, it means no titration has occurred yet, no reaction has happened. So at this moment, it's just a pure acetic acid solution. And if we know the pH, we can definitely calculate its K. So we can directly use the three-stage method. pH equals 3, so the corresponding hydrogen ion concentration is 10 to the power of negative 3. Since it's an equimolar dissociation, the resulting acetate ion must also be 10 to the power of negative 3. The problem gives the initial acetic acid concentration as 0.1 moles per liter. Since it dissociated by 10 to the power of negative 3, the remaining concentration is 0.1 minus 10 to the power of negative 3. But here we can ignore this value because the ratio is 100-fold, so it can be ignored. So it's just 0.1. Once we have the concentrations of these three species, we plug them into the Chi expression for acetic acid to calculate it. 0.1 is the denominator. The numerator is 10 to the minus 3 times 10 to the minus 3. After calculating K is 10 to the minus 5. This is approximate. The actual K for acetic acid is 1.75 times 10 to the minus 5. If you find the three-stage method too complicated here, you can just use a formula directly. K equals, at the starting point, the square of the hydrogen ion concentration divided by the initial concentration of the acid. That solves it directly. Next up, the particle distribution coefficient graph. Why are these 2 points the K points? First, pay attention. What does this graph represent? It represents the diprotic acid, H2A, as the pH increases. This means you're adding a base to it, right? The acid is continuously neutralized by the base. H2A is continuously reacted away, forming HA minus ion. Then the HA minus ion is reacted away, forming A2 minus ion, right? It's a process like this. So these 2 points, since they are intersection points, what does that mean? Doesn't it mean that at this point, hey, their concentrations are equal? The next point means their concentrations are equal. Since it's a diprotic acid, the corresponding equilibrium constants are K1 and K2. After writing it out, you'll find that once the concentration of H2A equals the concentration of HA minus, they cancel out and you're left with just the hydrogen ion concentration. So the pH at this point corresponds to the value of Ca1, doesn't it? So if the pH is 1.2, the corresponding hydrogen ion concentration is 10 to the power of negative 1.2, which equals Ca1. And the next point, by the same logic, K2 equals 10 to the power of negative 4.2, and that solves it directly. Once you've calculated K, the rest of the problem is straightforward. Now look at this problem. It's simple. Option B says log K2 is negative 4.2, which is correct. Let's check the other options. When pH is 1.2, their concentrations are equal, no problem. When pH is 2.7, we compare concentrations. Find the x-coordinate and draw a vertical line. It matches the intersection, where diprotic acid H2A equals the concentration of A2 minus ion, which is at its maximum here, no problem. For option D, when pH is 4.2, the two are equal, no problem. This is the intersection. But is it equal to the hydrogen ion concentration? Not necessarily. So D is incorrect. Now, this is the particle distribution coefficient diagram. The most crucial thing is that we find that once this kind of graph is drawn, we can compare the concentrations of the acid's corresponding particles at any pH, right? You can just draw a vertical line to compare them. This is very crucial, and we'll use it later. Okay, next, let's look at the hardest one. The logarithmic plot. Key points of a logarithmic plot are where x or y is 0. In this graph, it still shows titration of a diprotic acid, so the equilibrium constants are still K1 and K2. Where x is 0, drawing a vertical line gives these 2 points. So what does it mean when the x-coordinate is 0? It means this value is 0, right? But this value is inside a log function. Log of what equals 0? Isn't it log of 1 equals 0? This means that at this moment, the ratio of these two is equal to 1. And doesn't being equal to 1 mean the numerator and denominator are equal? So if you look at the equilibrium constant expression below, when they are equal, they cancel out again, leaving only the hydrogen ion concentration. So using the pH at this point, we can again calculate the Ca1 and Ca2. So the corresponding K should be 10 to the power of negative 4.4, and the other is 10 to the power of negative 5.4, right? So the larger one must be Ca1, and the smaller one is Ca2. Therefore, this line segment in the bottom right should correspond to Ca1, and the one in the top left should be Ca2. so we can determine option B directly. Curve N represents the relationship of this ratio, right? And this ratio multiplied by the hydrogen ion is K1, isn't it? So it corresponds to K1, no problem. For option A, it tells us the order of magnitude for Ca2 is 10 to the negative 6th. Note that this is about the concept of order of magnitude. Ca2 is 10 to the negative 5.4, so it corresponds to the order of magnitude of 10 to the negative 6th, no problem. Next, let's move on to C and D. Hey, it asks us to compare the particle concentrations. Generally, don't we have to write out all the equilibria at this point and then compare them step by step, right? But as we just said, using the particle distribution coefficient diagram, we can compare the particle concentrations at any given pH. So how do we draw the particle distribution diagram now? We happen to know the Ca1 and Ca2 at this point, don't we? So don't they correspond to these two intersection points? The particle distribution diagram can be drawn, right? The x-coordinates of these two intersection points are 4.4 and 5.4, respectively, right? So option C tells us that in the NHX solution, the hydrogen ion concentration is greater than the hydroxide ion concentration. So we can directly find the point where HX is abundant. At this point, the pH of the solution is between 4.4 and 5.4, making it acidic, right? Therefore, the hydrogen ion concentration is greater than the hydroxide ion concentration, which is correct. Option D, when the mixed solution is neutral at pH equals 7, it asks us to compare. Hey, just find pH equals 7 and draw a vertical line. You'll find that the X2 minus ion should be the most abundant of the three at this point. It's definitely greater than HX minus. So this order is wrong. It's completely reversed, right? You can solve it just by drawing the graph. Let's do another problem. Note that this one is a triprotic weak acid, so there will be K1, K2, and K3, right? Look at the graph and find the 0 points. There are 3 0 points. The coordinates directly correspond to the K values. So the K values, K1, K2, and K3 should be 10 to the negative 2.25, 10 to the negative 6.77, and 10 to the negative 11.4, respectively. And with that, it's solved.